Again, welcome everybody. This is the first seminar of this academic year, so in September 2025. And today we have Patrick Urban from Cologne Chip that will talk about the GateMate FPGA, a European 28 nanometer FPGA with an open source toolchain and radiation qualification results. Patrick holds degrees in applied mathematics, informatics, and computer engineering with a focus on network and embedded system. Since 2012, he has been part of the engineering team at Cologne Chip, where he contributes to the development of the GateMate FPGA family. Alongside his work in development and technical support, he also serves as the company's contact person for open source tools, as well as for application in radiation hardened environments. So please, Fadik, you can start.
Okay. Thank you very much for the kind introduction, Davide. And also a special thanks to you and, of course, to the organizers of the FDF to make this seminar here possible. Before I dive in, let me just say this is not going to be a sales presentation. As you heard, I am an engineer myself, and today I want to share with you what we've actually built, what we've tested, and what we've learned over the past few years. And as you just heard, my talk is about GateMate. That's a European 28 nanometer FPGA that stands out with an open source toolchain, which is unique. What I'd like to do today is not just walk through the architecture of the chip, but we will also do some live examples, and I have some hardware prepared for that here so that we can just have a very nice hands-on how the tools look like, how you can control them, what the results are like. And since we are here in an FDF seminar, which is very close cooperation with CERN, we will also take a look at the radiation qualification results that we've done over the past few years. Some of you might have never heard about how to actually do such a radiation qualification. And I think that it's going to be very exciting just to learn this about. So before we dive in, let me just give you a very brief overview about Cologne Chip. Actually, I can't see who is in the audience right now. But typically, I ask who has ever heard about Cologne Chip before. And lots of people think that we are still a startup, but that's not the case. So Cologne Chip has been funded in 1994, which means that we have over 30 years experience in semiconductor business. In the 90s, we had something similar as we had in the COVID pandemics, when it came to a shortage of semiconductor parts on the market. And that was the time when we presented the very first single chip solution for ISDN. At these times, you still had to buy multiple chips to build a single application for telecommunication systems, like FIFO chips, a processor chip, some S-null converter chips, and so on. However, if only one single piece was missing, then you couldn't just build your telephone system. And that's when we came up with the very first single chip solution. You see some of our chips here on the right-hand side. It is very remarkable that we have the Cologne Cathedral on it, and we are in lots of integrated access devices by now. So that means if you have some routers from Vodafone, Telefonica, U2, if you have some telephone systems from Auerswald, you can just open them up, and if you see the Cologne Cathedral, you see that you have been using our technology as well. We always have been using FPGAs for prototyping of our chips. And by the same time, we also implemented our very own ASIC PNR tool, just to save some money on licenses for Cadence or Synopsys software. And at some point in 2013, by the way, I joined the team in 2012, we came to the idea that it might make sense with the knowledge of having a place and route tool and have been using FPGAs before. why shouldn't we make an European FPGA? And that's when we came up with the GateMate series in 2020. So just to sum this up, this is the only sales slide that I have here. We have lots of experience over lots of years. We have something that we call a same-day delivery. So that means if you need some chips, may it be telecommunication chips or FPGAs, we typically send them on the same day. So something like having a chip shortage has never been the case here at Cologne Chip. And that's also thanks to the supply chain that we have, because the chips that we do are actually built in Germany. Today, I will give you a very brief introduction to the architecture and, of course, to the tool chain. And I will also show you what boards are currently available so that you can just start some of your designs. After that, and that's maybe the most interesting part, we will have a brief hands-on on the tools. So I will show you 2 examples where we just run the synthesis tool, where we run NextPNR as an implementation tool, and we will actually see something on the hardware here. I will also show you some of our IP that we have from a third party, which you can use. And after that, we will jump into the topic of radiation qualification. Just for you as a introduction into that, about 2 years ago, we had a cooperation, or we still have a cooperation with the Fachhochschule Dortmund, and they've sent a student who did his master's thesis at the CERN, and they tried to qualify our chips if they can use them at CERN. And they found out that even if we had a CMOS, a bulk CMOS process for our chips, that they were pretty reliable during the radiation testing. And that led us to some more qualification campaigns that we just had after that. And I will show you how we did the test setup for that. I will show you some of the images that we did during the campaigns in the test chambers. And of course, I will also show you some of the results for that. For those who have been in my talks before, I'm pretty sure that you've already seen the slide. I still like it very much because it contains all information in a single slide that you need to know about the GateMate chip. So on the right-hand side, you see a fairly simplified diagram of the GateMate. And what you can see here right in the middle are the so-called logic tiles. This is an 8x8-bit logic element, which is the so-called CPE. So there's a total of 64 CPEs per tile. And the center here has a total of 20,000 so-called programmable elements, or CPEs. This whole silicon here is built in the 28 nanometer process, which is called super low power at Global Foundries, which is Fab 1 in Dresden. So this is truly a made in Europe or made in Germany chip that we are seeing here. What is a little bit different to other vendors on the market is that our lookup tables don't have 4 inputs or 6 inputs, but we have 8 inputs, or a total of up to 8 inputs per CPE. I have another slide that will highlight some of the details there and what's so special about them. I must honestly say they are pretty sophisticated, and they also contain a part that is for the arithmetics unit, which does not only contain a 2-bit adder, but also a 2x2-bit multiplier. Those multipliers are connected to the neighboring CPE cells, and this way it is possible to build arbitrary sized multipliers anywhere in the chip and at any size. That's why you can also see that there are no DSP slices at all, but only block RAM cells here. There's a total of 32 block RAM cells, and they have pretty much all the features that you know from the other vendors as well. So they have true dual port support, simple dual port support. There's a FIFO built in. They have ECC output registers, pretty much everything that you know. Around this center part here, which contains the logic fabric, we have the GPIO cells. There is a total of 162 GPIO cells, which can be either configured as a single input GPIO or as a differential pair, which gives you a total of 81 pairs on the chip. we designed all cells to be the same as the other cells. So that means there is not only a single bank that can have LVDS support or some special support for some features. Every cell can be used as an LVDS pair, and every cell, of course, also has DDR registers. There's a total of 4 PLLs, like digital clocks here on the chip, with a maximum clock frequency of about 450 megahertz. And that's also the maximum clock frequency that you could achieve inside of the CPE fabric here. We are still talking about a 28 nanometer chip here. However, this always depends on, of course, placement, routing, static timing analysis, and such. But just to give you a rough idea, 450 megahertz is something that you could achieve with this technology here. On the top left, you see the so-called SerDes, which is a serializer deserializer. This is more or less like the GTP that you know from the Xilinx series, which can be used for either PCI Express, Gigabit Ethernet, or whatever. I will also show you another slide that highlights some of the features of this SerDes block here. We don't sell chips as industrial chips or automotive chips. Every chip in our or that you can buy from our stock is specified for the temperature range of -40 degrees up to 125 degrees. Again, since we are in 28 nanometers here, the core voltage for the block here is 0.9 volt to 1.1 volts. So if you have a design that requires some more or some better timings, then you can easily just switch over to 1.1 volt and have it overclocked. Or if you have an application where you are focusing on low power consumption, you can even go down to 0.9 volt in the core. The I/O voltages are specified from 1.2 volt to 2.5 volts. That's something that people have, well, complained about. But just to give you some background information on that, with the proceedings in chip manufacturing, like going deep submicron, 16 nanometer, 7 nanometer, and such, it gets harder and harder to build 3.3 volt tolerant cells. It is still possible. However, timings are getting really worse there. So we decided to go with 2.5 volts. However, we did long-term tests on that. And we have another test design running here in our lab that has been running for almost a year now at 3.6 volts in absolute worst case scenarios. So it has the maximum driver strength, it has an increased temperature range, it is running at 200 megahertz, it is running at 3.6 volts, and the cells are still alive. And you couldn't see so much of an aging of the cell. So if you need some more information about that, we can talk about that later on. What is somewhat or stands out for us is that we are using an open source toolchain. We will talk about this later. And we have a series of chip, what we call GateMate A1, GateMate A2, and GateMate A4. This is a patented concept that we have and what you can see here on the right-hand side. This grayish part here is the so-called scribe line on the wafer. Typically, you cut it here and there to get your die and then package it. What we did is we still kept interconnections from one die to another, and there's a total of more than 2,000 signals that go from one die to another and back. And this way it is possible to communicate with the other die here as well. And just by not cutting at those scribe lines, it is possible to build larger chips. And that's what you can see here on this slide. GateMate A1 is just a single die in a package. GateMate A2 still has two dies which are still interconnected in silicon. A4 the same, still interconnected in silicon. And all these three chips are pin compatible. So that means if you start evaluating your design right now and find out that the resource utilization gets worse and worse, you can literally unsolder the chip and use the A2. You can even go the other way around. Think of an application where you want to build a low-cost variant. And you find out, well, after reducing some of my code, I found out that I can switch from an A2 to an A1. This is possible here. These are some more features here. There are a couple of things that we already talked about. However, for today, it is interesting to talk about the instant on configuration. It only takes a couple of milliseconds to boot the chip up, even since we have an SRAM-based FPGA, but we can use a quad I/O configuration bus interface that runs at least at 100 megahertz, which allows us to configure it like out of the box. There's also a bitstream scrubber. That's something that we haven't published yet, but every chip has this feature, which was very important in the radiation testing that we did. This definitely made a difference here, but we will see this later. Before I usually start designing something with my FPGAs, I don't have the board on my desk and start playing with the hardware. The first thing that I will do is, of course, start the software and install the toolchain. As I said, we are the very first to have an A to Z open source flow here for our FPGAs, or actively support it. You probably already know the YOSIS framework or NextPNR. They have great support for lattice FPGAs. The synthesis here in our case, which we built around YOSIS, has multiple passes. There's one pass for the lattice FPGAs like SynthECP5. There are also passes for Xilinx FPGAs, but there's also a pass for the GateMate FPGAs that converts your sources, which can be either Verilog codes or GHDL can be used for VHDL synthesis, generates a primitive mapping or a netlist with primitives that can be used later on in the implementation process. YOSIS itself generates a JSON netlist with all the primitives, but it can also generate netlists in a Verilog or with a pull request in a VHDL format so that you can perform post-synthesis simulations with that. After the YOSIS pass, we switch over to the implementation, which is handled by NextPNR. Actually, this is NextPNR Himbechel that works together with the so-called Project Peppercorn repository. This is a repository that contains chip database information like timings, the architecture of the GateMate, some more tools to pack bit streams so that NextPNR knows how to place and map something in the chip, and of course, how to do the timing analysis and such. NextPNR generates a bit file, which can then be configured to our FPGA. We typically advise you to use OpenFPGA Loader for it. This is again a tool that has support for pretty much every FPGA that you can get from every vendor. And they also have great support for our GateMate FPGAs so that you can configure it either using the JTAG interface of the chip. You can also use the passive SPI interface for the chip, or you can also just store it in an external flash so that you can start your FPGA from it. On the right-hand side, you can see the graphical user interface for NextPNR Himbechel. Right here in the device viewer, you see, this is going in a loop here. You see how NextPNR places primitives and CPEs in the chip and then performs some kind of a simulated refining with simulated annealing to fit it inside the FPGA. I think this is a design for a very basic VGA display design that I think shows NyanCat or something like that. So you can clearly see the blockrams here. You can see, of course, the CPEs that are being mapped here. The blockram is used for ROMs. It is used for a frame buffer and such. So not a huge design, but have you counted the time? How long it takes here? It's just a few seconds. And that's something that is very special about these tools. They are extremely fast. And of course, since they are open source, they are also available for free. And there is the very famous OSS catsuit here. I also added a link here. You can also just scan the QR code here up there. This is about 500 megabytes. If you download it, it runs on Apple machines with ARM CPUs or with Intel CPUs. It also runs on Linux machines on ARM or on Intel CPUs, but you can also run it on Windows if you'd like to. So there are daily builds there, and you can just download them there for free. Now, what is so special about the logic element that we have here? As I already said, main difference is that we don't only have 4 inputs or 6 inputs, but 8 inputs. However, you can split them up to have 2 4 independent logic cells here. And with the GateMate A1, which has 20,000 logic cells, you would have 40,000 4 input functions for your design. The black box here is the arithmetic unit, and this one is connected to the so-called CP lines, which are highlighted in green here. CP lines are direct interconnections from one CPE to another, so they don't need to go through the logic routing unit or fabric to reach another CPE, but they are the direct interconnects. And with these direct interconnects, you can build horizontal or vertical adders, but you can also use them to build the 2x2-bit multipliers here. And that's what you can see here. On the right-hand side, you see how we implement a multiplier in the CPE array. On this checkerboard pattern here, each block would be a single CPE. Blue CPEs are actually CPEs that are being used as a multiplier. Green CPEs are just flip-flops for input and output pipelining stages. And as you can already see, since this is an 18 by 8-bit multiplier, you see that it grows either on the x-axis or in the vertical path here. It is true that if you increase multiplier sizes, that this definitely affects timing in the chip. And that's what I wanted to highlight here on the left-hand side. This is an 8 by 8-bit multiplier that has been implemented for the low power mode, which is 0.9 volt core voltage, the echo mode, which is 1 volt, and the speed mode, like the overclock mode, where you can reach higher clock frequencies. We also did this for the 3 corners: worst, typical, and best from the corner. So like the speed grades for the chips, which is also the temperature of the chip. So at lower temperature, the chip performs less good than at higher temperatures here. If you compare an 8 by 8-bit multiplier at 25 degrees and 1 volt core voltages, you would basically achieve 175 megahertz for your multiplier. If you increase it, you can clearly see that this maximum clock frequency drops here. However, the B vector here is the critical path in the design. And that's what you can see here on the right. This is an 18 by 8-bit multiplier. So we just reduced the B vector here. And you can see timings are pretty much the same as for the 8 by 8-bit multiplier. And that's what you can see in lots of designs. So typically in DSP designs, filter designs and such, it is very likely that you don't have a 32 by 32-bit multiplier, but sometimes 16 by 6-bit, 16 by 4-bit, 18 by 4-bit, something like that. And if the B vector is small, you get high frequencies out of it. The blockgram is something that we already talked about. You can clearly see that we have this, I would say, onion structure here with multiple modes until the signal reaches the actual RAM macro in the chip. So this is a 40K blockram cell, but you can also split them into 2 independent 20K cells, which gives you a total of 64 blockrams in the design later on. And as I already said, they have true dual port support, they have simple dual port support. We have a FIFO here, which can be run in a synchronous or an asynchronous manner. We also have ECCs here, and there's also some interconnects between all blockram cells, which gives you the ability, if you have some design that consumes more than a 40K blockram cell for a single blockram that you described, then we can use those signals here as a cascading feature to build larger blockrams without using the logic resource units here in front of the programs. The SerDes is something that you can also see in other vendors. The only difference here is that we have a larger data path. So with a GTP, you typically have 40 bits for the data path in the TX and RX direction. However, we decided to go with an 80-bit data path. This is very relaxing at high frequencies for the CPE fabric. So that means if you run your design at 5 gigabit per second here in the analog world, the clock frequency for the CPE is only 62 megahertz roundabout. And this is very relaxing for the chip here. We offer those SerDes blocks as 5 gigabits blocks. And you can clearly see we have emphasis controls. There's an iScan feature in it. We have, of course, AP10B encoders. There's even a PRBS generator and a checker so that you can check the signal integrity of the SerDes design. But there's also an ADPLL that is highly configurable. On the right-hand side, you can see if you run the SerDes at 100 megahertz with a reference clock or 125 megahertz, what kind of configurations you can achieve with the SerDes. So this is the maximum currently in spec. You could configure the SerDes to run at 5 gigabit per second. However, we currently sell all chips as slow chips. So there are actually no speed grades right now. You can be lucky and get a fast chip here. But if you have one of the fast chips, it is even possible to configure higher clock frequencies here. The maximum that you could theoretically configure for the SerDes is 10 gigabit per second or 12.5 gigabit per second. The SerDes itself is extremely complicated. If you are a SerDes designer, you probably know that. We have a very, very large section in our documentation that only handles the SerDes. And if you have some questions about that, well, you can just ask me later on here. Now let's talk about some of the available boards currently on the market. This is the official GateMate evaluation board, which can carry either the GateMate A1, A2, or A4. There's also a PMOD header here. We have lots of GPIOs that you can access here. And there's, of course, a programmer here on board, which is just an FTDI. You can, by the way, use any FTDI that you have laying around there that can talk SPI or JTAG and configure the FPGA. So there's no need to buy a proprietary programmer device for our chips here. You even have access to the SerDes port here using the SMA adapters, and you can configure the core voltages. Here is a shunt. So if you want to do some power measurements with the chip, you can just select different core voltages and see how the chip performs here. This is the official evaluation board. What I really love is what the open source community is currently doing. And this is the Olimex evaluation board. This one here is a 50 euro board that you can get, which can also carry either GateMate A1. Currently, it does not have the A2, but it has lots of extensions that you can attach to it. So if you'd like to, I also added the links for the repositories here. You can have HDMI connectors for that. You can have gigabit Ethernet transceivers for it. There's even a camera interface for it. So anything that you would like to attach to the board, that's something that you can do with the Olimex boards here. There's another board that also has lots of interfaces, and that is the ULX 5M. Again, if you'd like to, I highly recommend just to take a look at the repository here. This is a Raspberry Pi compute module that is compatible to any of the Raspberry Pi carrier boards. And those boards, honestly speaking, are extremely cheap. So you can get them for 20 or 30 euros at Amazon and just attach the board here. So that means for very little money, you get lots of interfaces with the GateMate, which even has an SD-RAM controller here. It has a gigabit Ethernet PHY. It has, of course, the clocks here for the gigabit transceiver on board so that you can do PCI Express. It has interfaces for the cameras, of course. That's something that we never mentioned before. You can use any GPIO on the GateMate to run a camera device on it. And there are some example designs. If you'd like to, you can just contact me. It is pretty easy just to connect a camera that runs MIPI interfaces with the GateMate. We had a similar solution about a year ago that used a trick to run the low power and high speed modes for the MIPI interfaces. We no longer need this right now. So with a single pair, it is possible to run a camera on it. I already explained that we have a huge IP catalog with support in the so-called LightX framework. Pretty sure some of you have already heard about this. This is actually a diagram that I got from their repository site page. And you can imagine that LightX is more or less a framework that is a Python-controlled software where you can, I always say, play Lego with it. It gives you the ability to generate code that can be run through our open source toolchain. And this way it is possible to implement some IP in it. LightX has a very nice interface to almost all FPGA toolchains that are available, even from other vendor tools. They also have an interface for CPU toolchains, because with LightX it is possible to generate SoC designs. And if you generate an FPGA design, it always makes sense to also generate some firmware that runs later on the SoC that you just generated. LightX also provides so-called board files and platform files. The board files currently hold, as far as I remember, more than 200 different boards from Digiland, from Olimex, and there are also our GateMate boards supported, like the official evaluation board, the Olimex board, or the ULX board, which is currently a pull request or will be a pull request. And it basically describes what the board is capable of. So, for instance, the Olimex board has an adapter for HDMI. It has an RGMII interface. The GateMate board has an external HyperRAM on board. So this is what you can just describe in those files here. Now, what makes LightX so powerful is the so-called cores ecosystem. You can also see it on the right-hand side. So these are different repositories that holds IPs for different CPU cores and for lots of periphery devices that you can attach to it. Just to give you an example, these are only a couple of CPUs that are supported in LightX, and I'm pretty sure that you recognize that there is VexRisk-V, Pico-RV, there's even Neo-RV32, the award-winning Surf. So there are lots of cores available in the LightX catalog that you can easily attach to some different IPs like Ethernet controllers, PCI Express, there's an SPI controller. So lots of things that you can just attach to it without having to write a single code line in Verilog or VHDL. And that's something that I will show you in the hands-on, which starts now. So let me just switch over to my screen here, and I will just open let me just zoom in. So this is visual code with an example design. Kudos to Gwen, who published this on his GitHub repository. This is a design for an HDMI controller, which basically just takes an external clock reference signal and generates an HDMI signal using TMDS encoding to draw some images on an external screen. Let me just, yes.
Maybe it's worth to zoom in a little bit more, unless people have
sorry.
a
Yes,
large screen, it will be
I have a
difficult to
4K
see.
screen.
That's perfect. Thank you.
Thanks for the hint. So what I already showed is that we have an input with an external reference clock. We have some outputs for the encoded TMDS signals. And this is basically built around the differential pairs that we have here. There's also a PLL that generates a 125 megahertz clock for the TMDS signals here. it will also generate a clock that is divided by 5, which is 25 megahertz for the internal VGA controller, which you can see here. Basically, the VGA controller just generates the the VSync, HSync signals and such. There is also a block here that generates some image. You will see it later. And of course, there's also the DVI core, which is basically a 10-to-1 serializer, and the ODDR flops for the GateMate that just handle the serialization of the data. On the right-hand side, I just wrote down a brief quick start, what you can run with our toolchain here. So basically, if you want to synthesize some Verilog code, then there are some, let me just scroll over here. You would typically use Yosys for that. Oops. Let me just close that here. No, we have a choice. Sorry. That's better. With Yosys, you can generate, of course, a log file. You can also tell it to be quiet so that it does not print anything on the screen. And then you can pass some parameters to it. You can tell it to read your Verilog codes. You can even add GHDL there just to read some VHDL codes. And then that's something that you probably remember if you have ever worked with Yosys before, that there are multiple passes for different architectures, like SynthECP5 or SynthIce40 for the lattice designs. There's also SynthGoWin. So there are different passes for different architectures here. And of course, there's also a SynthGateMate pass. With top, you specify the top module. With LUT3, you enable the LUT3 support. So it disables LUT4, LUT6 and such, and it maps directly into the LUT3 that we have. And you can, of course, add some more parameters like please don't use max8, please don't use hardware multipliers. That's something that you can do. You don't have to do that. So if you just remove no mult, then you will see that it also maps to the hardware multipliers in the CPEs. And of course, it will just write the netlist so that you can export the files here for the place and route tool.
There's a
PNR is
question
almost yes.
from Chris. What DVI resolution does the code support? And there's also a question if this repository is available for people.
Yes, this repository is available. Yes, it is. I can just send it in the chat after the meeting if you don't mind.
Sure, thank you.
The clock frequency or the design for HDMI. So I have a very cheap display here. This is currently 480p. That's something that you can already see from the clock here. So if you have a design that runs at 720p, this would be a 374 megahertz clock. If you run it at 60 hertz, or if you run 1080p at 30 hertz, that would also be 370-ish megahertz here. After the synthesis, you can run the implementation with NextPNR. Here you can specify what device you want to use. So that can be either the GateMate A1 or A2. Data, this could also be A4 and such. Of course, you have to specify the input file. And then you can specify the constraints files. So you can also attach SDC files. The SDC format is, I guess, fairly now. However, CCF is our own constraints file for pin constraints. I will just show an example later on. After NextPNR, we have to pack it because NextPNR generates a text file as the bit stream so that humans can actually read it. GateMate can't, so you still have to convert it into a bit file. That's what GMPack is doing. And I also double-clicked it, but never mind. After that, you can configure the FPGA. As I already said, you can use OpenFPGA Loader to either configure it using the JTAG or SPI, or you can also store it in an external flash. And OpenFPGA Loader will automatically detect by its ID, a vendor ID and such, what kind of flash you are using and what kind and how it needs to handle the external flash. Let me switch over to the CCF file. So we already have the source codes here. We also need to specify the pins that we have here. This is very easy. So you have to specify the net. This is the net name that we have in our Verilog or VHDL code. And then we can specify the location for the pin. In our case, this would be the North Bank part B, pin A4 or B4. You can already see TMDS is a differential pair, so it has a positive and a negative signal. And this is A and B for the positive and negative signals here. You can also concatenate some more parameters to it. We just documented them here. If you have an input, you can, for instance, define a Schmidt trigger here. You can also generate or implement pull-ups, pull-downs, keeper. For better EMI, you can also control the slew rate. It is, of course, possible to change the drive strength for the signals with up to 12 milliamps. There is a static delay of nominal 50 picoseconds that you can configure using the delay parameters here. And of course, for the LVDS or the differential pairs, it is also possible to change the driver strength from the default of 3.2 milliamps to 6.4 milliamps just to increase the swing of the signals in this case. I disabled it here because for TMDS signals or HDMI, it is required to have a swing of 300 to 600 millivolts, as far as I remember. And that's easily achievable with our GPIOs if they are configured to 1.8 volt or 2.5 volts without the additional driver strength settings here. Now, I must admit, I don't remember all those parameters here. That's a little bit too hard for me. So what we did is we also implemented a makefile to make things easier. And for that, I downloaded the OSS catsuit. And first thing that we need to do is we need to source the environment to have the tools here available. So what we do is we just source the environment, and then you can see that we are now in the OSS catsuit. With being in the environment here, you now have access to all the tools like Yosys. If you just run it, you see, okay, I am in Yosys here. Nice. I also added some examples here. So if we just switch over to the examples, GateMate, and then the color bar example here, there we also have a makefile here. And for the makefile, you only need to remember 3 commands. First thing, make synthesis. Maybe we should make it clear before that.
Meanwhile, there are two more questions. Will the GateMate feature faster transceivers in the future or soon?
So as I already said, 5 gigabit per second is currently what we offer. You can be lucky and get one of the faster chips. That's something that we need to logistically handle before that. So we can sell chips at a faster speed rate. However, from a logistical point of view, currently this is just too much overhead for us. So you could achieve, I had some designs running at 8 gigabit per second. So this is definitely possible with a typical chip, but it would never go above the 10 or 12.5 gigabit per second. So we highly suggest just to stay with 5 gigabit per second. So now I got it here. We can just run make synthesis, what you can see here. And if you don't mind, you can just start counting how long it takes just to run the tools. Okay, done. This was synthesis. It only took a couple of seconds, and you can already see from the report that it had found some adder cells, 2 BUFFs. Well, of course, this is a 125 megahertz clock and a 25 megahertz clock. There are some flip-flops. There are some LUTs inside. There's also an LVDS output buffer and such, so pretty easy. After that, we can just run make implementation. After that, it will start next PNR. And here again, it doesn't really take long just to implement the full design. That's it. if we can just take a look at the log files that it just generated, it gives you some information about the maximum clock frequency of the clocks. So in this case, we need 125 megahertz for the for the TMDS generator. It achieved 204 megahertz, which is fine. For the not so fast part, which is the VGA, we achieve 35 megahertz, which is also fine enough here. You also get some critical path reports here if you want to improve your design in the source code, so you can see where exactly in the code is the part that you are looking for, so that you can just find the registers and the LUTs involved just to improve the design. And there's of course also a brief overview about the device utilization. This is, to be honest, not a very hard design. So the LUTs that we are currently using is 1115. That is only 2% of the full chip here. So it's not that much. We can even take a look at it if we just run make impl with graphical user interface. Then we will also get NextPNR Himbekel with the device viewer here, and you can just zoom in. Then you can see, well, of course, here are the CPEs. There are the blockgram cells and such. And in this graphical user interface, you can also just start the packer, of course. Packer will only allocate some of the GPIOs here. After that, you can start the PNR tool. Then it will optimize it, so it will find an initial placement, then refine it, and that's it. So basically everything that you can do on the console is also possible here. It is even possible, sorry, I can't zoom in here, to use the console here or the terminal to run some Python code. So if you just import sys or something like that, this is still possible here using the terminal in NextPNR. After that, we can, of course, configure the FPGA. So it generated a bit file. That's what you can see here on the left-hand side. So there's the bit file that we just generated. And if we just type make JTAG, it configures the FPGA. And not sure if you can see, still can see my display here. Now we have something on our screen that is just bouncing some HDMI signals here with the OLIM export. So pretty easy just to start it. If you run it from A to Z, it's only a couple of seconds just to run synthesis, implementation, and such. To show you how this works with a slightly more advanced design, I have something from the LightX catalog here. This is again a design that runs on the OLIM export, and this is basically the file that we had that describes the light export for the OLIM export here. So it has some PLLs that are configured here. It has a video terminal. You can even get some more information about it, what kind of parameters it has. But you can also just type in Python olimex --7. This will give you lots of information of what you can do with the LightX catalog here. For instance, you can say, please take another system clock here. Currently, it is configured to this clock frequency here. You can also say, please use a video file, either GPDI, which is HDMI. Please use a VGA terminal here. You can also say, well, please use an Ethernet controller for that. Pretty easy to do. So that means if you want to design something here, you can, maybe I can just clean it. You can just say make, sorry, not make. Please build a design. Please also load it into my FPGA. We take the CPU type, maybe VexRisk5. Please use it as a light variant. So that means CPU minus variant light. And of course, please use another toolchain, which is Peppercorn. Now it will generate some C code because we are currently, or we will also be able to see something in a terminal. There is some firmware running inside the chip. This is still the C compiler. By the way, you have to only run it once. And after that, as you can already see, we are now in the synthesis. Now it's in place and route. We can already take a look at the device utilization. So here we can see, of course, this device design is a little larger. However, it's still only 40% of the chip. So it's not that much. And we even had a CPU here that has a external memory interface, a UART interface. There's, of course, some extensions like the multiplier extensions and such. So there's pretty much going on in the chip here. Maximum clock frequency right now here is 40 megahertz. That's what it achieved here. Now it's in routing. I can already start a terminal. I will also zoom in. And it already booted. So this is what you can see from the GateMate here. So it is a VEX RISC-V running at 24 megahertz. It has some little RAM here. And now you can just do something in the bootloader here. So you can just ask it for help. So this is some C code running in the CPU of the GateMate right now. There you can do some, let's say, memory speed tests. Do it from 1 to 124. Then it will just do some tests here. And there are lots of interfaces that you can use to upload some designs or firmware. You can either use a serial interface, you can use an external SD card, you can use an Ethernet port for that. You could even use an SATA hard drive that you have connected to it if you have the PCI Express configured to it. So there are lots of things how to upload some code here. So the maximum clock frequency that it finally achieved on the design was 52 megahertz, which is fine for such a CPU. And yeah, this is basically what's going on in the Lytix catalog. Actually, I typically have some trainings about Lytix. They usually take like 1 or 2 hours. It's way too much for today, but let me just switch over to the presentation slide so that we can talk a little bit more about the radiation qualification. Again, those slides are available. So if you need some more information about how to install the tools, I just added some slides here and some notes how you can use those tools. Now let me switch over to the radiation qualification. So as I already said, what we did before was we started at CERN and did some primitive testing of the GateMate. So that means you are typically taking a look at all the primitives that your design has, like flip-flops, lookup tables, PLLs, blockrams and such, and see how it behaves under radiation. And for that, you need to generate or implement certain tests. Let me just highlight some of those tests here. On the left-hand side, you see a flip-flop test. Basically, this is a large shift register that is going through the chips or through the FPGA that has some initial values inside of the flip-flops. You do this without any radiation. And after the design or the chip has been initialized, you're just going to shoot at it. Very simple. And let it run for a certain time. And after that, you can just shift the shift register back. We have a tester FPGA that is sitting behind our FPGA that is just checking if the pattern that we just initialized inside those flip-flops is still the same. And with that, it is possible to see how many of the flip-flops have flipped during the radiation. There's something similar for the blockram tests. However, those are way more bits that we do here. So there are multiple blockrams here, and we always initialize them with some pattern, like with a checkerboard pattern, only ones, only zeros, something like that. We radiate it and read it back and check how many bits are flipped here. These are tests for single event effects. Another thing that we are currently looking at, or usually look at, is the total ionization doses. And for that, we implemented multiple ring oscillators in the FPGA. With multiple ring oscillators, it is possible to characterize them. So each ring oscillator would have a certain clock frequency that it's running at. And if you irradiate it after a longer time, you will see that there are some shifts in the clock frequency. However, this is not a single event effect. So this is an effect that you will see over a longer period, so because it is irradiated. But again, this is something that we definitely need to find out, because I don't want my FPGA to change its internal timings when it's in space or somewhere. The most complex test that we did is the config-ram test. Basically, this is the same test that you can do with the flip-flops with other vendors. However, in GateMate, this is not possible, because here it is not possible to read the configuration back. Once the configuration is stored in the GateMate, it is never possible to see it again. And for that, we built a very large XOR structure, which is also just a very long chain of 8 input XOR gates. And then we also irradiated it. We knew what bits are critical here, and this way it was possible to find out how many of the configuration bits flipped. There's also a more real-world example here from the ITC99 benchmark, which is basically some algorithm that is running in multiple cells. Then there's a huge multiplexer, and there's a golden reference on the tester FPGA that is constantly checking if all those cells here are doing the same stuff. This is the proton beam setup at the Paul Scherrer Institute. For those who have been using our FPGA boards before, you probably remember this is just our FPGA board, and we are simply just shooting the proton beam here on the chip. These are some of the results. Let me explain them in a little more detail. Very important to note, these results are not with the bitstream scrubber, so can be much better if we enable it. We have multiple FPGAs for microchip. There's also a Nano Explorer FPGA. There are some Xilinx FPGAs, and there's, of course, the GateMate FPGA. This is the block-ram test results. And what you can see here, typically you want to achieve a low cross-section. So lower means better. Interesting thing here is the Xilinx FPGAs are much better than the Nano Explorer FPGA, however, Nano Explorer. This is a Red Hat FPGA, so very weird here what's happening in those test cases here. GateMate even did not achieve that good results here, to be honest. However, we did some more tests in the upcoming campaigns. So these are just the results from this paper here, and they were much better. We think that we hit lots of the multiplexers that are outside of the block-ram cells, and this led to this increased value here. If we compare the flip-flop results, we are pretty good. So here again, some FPGAs from Microchip. There's a Nano Explorer FPGA, there's a Xilinx FPGA, and of course there's our Cologne chip FPGA, which is pretty good, to be honest. So we are almost at the same level as the Red Hat FPGAs here. There is a non-TMR, which is just a triplicating of modules, and a TMR version. If you enable TMR, it is typically a little better here. Same for the ITC99 test. Here we are on par with the other FPGAs like the Stratix designs here. We also did some TID tests, and for that we designed, or the students designed, a GateMate board. Basically, the Quatebo board here is a Red Hat carrier board. It contains only components that are Red Hat because it will be exposed to a lot of radiation, and it is possible just to activate those boards here. And only chip that is not Red Hat here is the poor GateMate in the middle here, which is being radiated for the TID designs. And what we found out is that up to 1 kilogray, we couldn't see anything happening in the chip here. Power consumption only started at about 4 kilogray here, which is, compared to other FPGAs, pretty good when it comes to TID. But we also did some other tests. If you are, for example, in space, single event effects, they are bad. That's not an issue, to be honest. It is always an issue, but you can fix them. If there's a single bit flip, well, you can find it out, you can fix it, that's it. What's really worse is a latch-up effect, because this will permanently damage your chip. And for that, we did some heavy ion test at UCL in Belgium. Here again, you can see our GateMate board. However, we did some modifications to it. heavy ions typically don't go through the package of the chip. And that's why we had to send it down. And we found a very nice package for the GateMate here, where we can just beam into the device here or into the package and directly hit the silicon area here of the chip. To be honest, those results are not yet public. They will be actually published tomorrow, but I can already tell we never saw a ledge-up effect here. So we did not hurt any of the FPGAs. Tests were pretty good, and it is very likely that we will do some more tests later on. That brings me to the last slide. What can we do with radiation qualification? And that's something that will happen this autumn here. The university in Hamburg already designed a board with a GateMate as a main processor here that is going to the so-called Pluto mission. This is not planet Pluto. This is in near orbit, but actually this is a research satellite that is actually being used for this FPGA here, which is an lattice FPGAs, and they are trying to evaluate it for some undervolting tests. And the GateMate basically has a RISC-V CPU on it. You can even have it as a TMR version of it, just to be on the safe side, which is more robust. You can also enable the bit stream scrubbing feature. You could do that, to be honest. It has an external hyper-RAM memory, and it's just doing some stimuli for the lattice FPGA in space to evaluate it. So yes, GateMate is going to space with that, what we've done so before. Again, we only had 50 minutes. It's lots of topics that we can talk about, but let me just stop sharing my screen. And I'm pretty sure that there are a couple of people still having some questions here.
Hi, Patrick. Very nice presentation. So there are a couple of questions that I didn't have the chance to ask before. So there is one from Scott. So have you verified the flow starting with VHDL, GHDL, and open source uses?
So there are two ways to do VHDL synthesis with uses. You could either use GHDL as a front end, or you can buy the proprietary cat suit from the Uses HQ team. They have support for, as far as I remember, the Verific VHDL compiler. I'm pretty sure some of the Uses guys are in here and they can tell you better. So there are two ways to synthesize VHDL code for it, but it is possible. So honestly speaking, in the German speaking part of the world and at universities, people tend to use VHDL. If you go over those borders, everyone is using Verilog for that. We never see anyone else doing any other languages, such as, only exception is LiteX, of course, like Migen, MOM, HDL and such. So we don't have any business partners or customers that ever used any other languages than VHDL or Verilog.
Okay, this is maybe a question more, so this is just a follow-up question on that. So do you see any difference in performance on the actual synthesized RTL when using VHDL or Verilog? Maybe this is more on the tool than on your design.
No, we won't, because Yosys handles the so-called RTL-IL. This is an Intel format how to describe logic gates, register sequences, and such. It never really cares if this was VHDL or Verilog before, because the front end that can be either Verilog, there's also another one for system Verilog, or VHDL with GHDL, it will automatically convert it to the RTL-IL if you have the plugin for that. And then it doesn't really make a difference if you have a VHDL design or a Verilog design. So we did some tests on that and never saw any differences there.
Yeah. Then there is a question from Jonas that wants to do Beam 4 beamforming in 32-bit arithmetic and is asking how fast is a 32-bit multiplier adder.
32-bit multiplier should achieve something about over 100 megahertz. That is still possible. There are a couple of more things that you can do to improve timing, by the way. So you can split multipliers up, add some adders to it. So if you, LiteX and VEX RISC-V are doing this, by the way. If you're doing a 32-bit multiplication, it just instantiates 4 16-bit multipliers just to increase timing and clock frequencies. So this is still possible. So lots of improvement mechanisms there.
Thank you. I see that Chris uploaded, texted in the chat the link to the repository. Maybe we can add it to the Indico agenda later on.
Thank you, Chris.
Are there any other questions? If not, I have just a curiosity, maybe if you can give us a hint in the future if you to plan to have, let's say, a chip with a, let's say, a smaller nanometer technology in the future. What's the plan?
So yeah, Cologne chip has a granted funding for a 7 nanometer chip. However, this still needs to be a 7 nanometer chip that is being produced in Europe. And as you probably know, there is no fab that goes below 22 nanometers right now. Only fab that we have in Germany or in Europe is the 22 FDSOI process from GlobalFoundries. It might be possible to use another fab outside the borders of Europe. However, this is still something that needs to be clarified. And so we have the grant for it, but there's still lots of bureaucracy that we need to do for that. Just for you as a side information, we started developing the GateMate in 2013. So it took 7 years to the final mask tape out, and we got the grant in 2015. So it's always a couple of years with lots of bureaucracy, of course, lots of engineering, lots of here and there to build such an FPGA. It's not an easy task, and that's probably why there are no other FPGA vendors in Europe right now, except for NanoExplore for Red Hat FPGAs.
Thank you. There is a follow-up from Jonas. What is the total radiation dose GateMate the GateMate FPGAs can sustain?
That's something that I need to check up. I don't have it in my slides right now. However, it was a lot. So at UCL, we shoot at it at the maximum performance that it could do. You can see single events, of course. However, what we did is we wanted to check for the ledge-up effects. So can we destroy the chip? And we never managed to do so. But you can just write me an email later on. So not sure if I'm still sharing my screen, but on the last slide, you see my mail address. You can just contact me there and then I will send you the numbers.
Okay, we have 2 more questions and then unfortunately we have to close.
I still have lots of time, so if you don't mind, we can just stay here.
Okay, I can also give the the room, or maybe if someone else can be the host. Or you can be the host, actually.
Sure, whoever wants to stay.
So Andreas asks if you are planning to produce with another producer. In theory, Infineon can be another foundry.
Not sure if they do 28 nanometers and below.
Okay.
So that depends. So as I said, only fab in Europe right now that can go low is only 22 nanometers. So I don't think that Infineon can reach such nodes right now. To be honest, again, GateMate is not intended for any space applications. This is actually not a Red Hat by design chip. We found out that it is doing pretty well. However, the market that we are currently targeting is more everything in industrial sectors like measurement, control, automatization, video processing. So that's what we are currently targeting here. Space is only a very, very small fraction what we are currently taking a look at, because no one is going to build 1 million satellites with GateMates in it. So it doesn't really make sense. You can easily look our prices up in DigiKey, and there you will see this is an FPGA that costs less than 20 euros. So it is an FPGA that is actually meant to be on a ground station and on terrestrial in parts here.
Okay, there is another question from Bob. Is this FPGA viable for consumer products? How long can you guarantee supply for this chip? And will future revisions be being backwards compatible?
We will offer it as long as GlobalFoundries produces it. That's a pretty easy answer. So just to give you an info about our other chips, the XHFC series, this was the last one that we brought to the market, started in 2008. We are still delivering them. The HFC series started somewhere around 2000, and we are still on the market with them. So long-term availability is something that we always try to focus on. So if GlobalFoundries is going to produce those chips for the next 10, 20, 30 years, then we will be able to offer them. However, this is still the same thing with other vendors. So if TSMC is going to stop their 28 nanometer process tomorrow, even Xilinx wouldn't be able to build those chips. So they have some guarantees for that. However, no one really knows what will happen tomorrow.
Understood. So I have to, unfortunately, to leave now, but please continue. I will just stop the recording right now.